Modulation topic that we are going to start studying from today uh, will be kind of in two parts. Okay, the first part is going to be the main fundamentals. And to actually appreciate the main fundamentals of modulation, demodulation system, or sometimes it is shortened as modem, modulation, mode part coming from the modulation, the transmitter, and dam coming from the receiver part, the demodulation part. Modem is the shortened form of what happens both at the transmitter and the receiver. Modem is actually, it has become a very common term now, right? I mean, at your home, when you get a Wi-Fi router, it is sometimes called Wi-Fi modem. Or if you have a set-top TV, then you need a modem for that as well. So modem is like, has become a common terminology, and what it is, what makes it work is what we are going to look at today. First part is going to be about the algorithmic part, okay, where we are going to understand somehow if the bits actually do get transmitted over the communication channel, and if they do get received, then how to actually demodulate them. And that is what actually we have already studied to some extent in the labs, and actually there was one question about that in the exam also. So when we do that first part, which we are going to call a simplified model or a basic model, we are going to ignore, in fact, this electromagnetic wave transmission entirely. And then once we kind of fully come to grips with that initial part, the basic simplified conceptual conceptual model of the modem, that is when we will add this additional layer of the concept which will bring in the electromagnetic wave theory. And it is at that point that we may actually have to study a little bit of Fourier transformation, a little bit of signals and systems. And so this modulations topic is going to get us to there as well. We are going to take we're going to switch the gears, so to speak. We are going to in a different landscape now. We are not going to be talking about channel coding or source coding anymore. This is a brand new topic. So hopefully you will like the change of scenery, so to speak. Okay, so let me get started. Okay, so we have actually, as I said, already studied a very simple model of a digital communication system. So there are some bits that are incoming to the modulation device. And these bits can come out of channel coding power. Or there may be some communication system which may not implement even the channel coding. Then they may come out of source coding. Or even if source coding is not there, it may come directly out of the source, the information source. It may be a digital camera or a video camera, or it may be some type of binary source. The point is that we are going to assume that the incoming information is always in terms of bits. And that we are going to denote as variable x. It's a random variable, as we have seen. Typically, it will be modeled as a Bernoulli 0.5 variable, meaning zeros and ones are equally likely. But it doesn't have to be that. You can have any value of q. In the BPSK modulation, and this is what the simplified model that we are going to study initially takes, is that x is equal to 1 is mapped to plus a volt, and x is equal to 0 is mapped to minus a volt. So you see there is no concept of electromagnetic wave here. We are just saying that bit 1 is transmitted using some positive volt, and bit 0 is transmitted using the negative of that. And so now bits have been turned into an actual physical signal. which can be measured using a voltmeter. And that is what we are going to call the transmitted modulated symbol. Okay, so modulated symbol has two polarities, plus A and minus A. If A is 1 volt, it will be plus 1 minus 1. If A is 10 volt, it will be plus 10 minus 10. And then it is this signal which gets transmitted over a communication channel, and the communication channel that we are going to consider is going to be mostly what is known as additive noise channel. It just adds to what is being transmitted. And a common type, as we have said earlier, is a Gaussian random variable with zero mean and certain variance. And so what the receiver gets is the summation of S and L. That is what the additive channel does. It adds to S. And then at the demodulator of a BPSK system, we have said that R equal to 0 is the decision boundary. And if R, the received signal, the received voltage is greater than 0, then we say that X hat is 1. We decide at the receiver that bit 1 was transmitted. If it is less than 0, we say bit 0 was transmitted. And that is how we generate the demodulated bit stream. Now, this is for the BPSK. There is an alternate modulation scheme which is called on-off keying, which is very similar to BPSK. The only change is that X equal to 0 is mapped to S equal to 0 volts. Meaning that whenever you want to transmit bit 0, you just switch off the transmitter. You don't transmit anything. That is the only change. And in that case, the decision boundary becomes A divided by 2. Why it is A divided by 2, I will let you figure it out. Now, I thought that I'll go over the math behind this demodulation rule for BPSK, which you can then extend to OOK. Because some of you had initially asked me that why this is the case, why R equal to 0 is a decision boundary. And I know that you had worked on it in your lab, and I think many of you actually know the answer to it. But for the sake of completeness, let us go over the math theory using the Bayesian theorem. So what we have to do essentially is to determine the odds in favor of X is equal to 1 when we get a particular received voltage R. So how do we do that? Well, remember in the Bayesian theory, we have to do the first thing that we have to define is the likelihood function. The likelihood of particular value at the channel output given X is equal to 0. And in case of additive Gaussian noise, this likelihood or the conditional PDF is just the PDF of Gaussian distribution. Except because minus A volt was transmitted when X is equal to 0 SN, the mean value becomes minus A. And therefore, the expression inside the exponent becomes R plus A. And this sigma n is just the standard deviation of the noise, and this is the overall expression of PDF. What is the condition likelihood function when X is equal to 0, X is equal to 1 is transmitted? Well, it is very similar, except the mean value now becomes plus A instead of minus A. And therefore, the only change is that this plus sign becomes minus. This comes directly out of the Gaussian PDF formula that we have studied earlier. So these are the two likelihood functions for X is equal to 0 and X is equal to 1. We have already said that the prior we are going to assume to be Q equal to 0.5. And therefore, if you recall, when the priors are equal, we don't have to even do maximum a posteriori detection. All we need to do is likelihood ratio detection, LRT, likelihood ratio test. That is called the maximum likelihood detector, which actually just evaluates this ratio and see whether it is bigger than or less than 1. So we need to just take the ratio of these two likelihood functions, which is pure math. By the way, before we do the math, let us look at what actually this signal looks like. Hemangi, you probably want to unmute yourself. I'm sorry, mute yourself. There is some echo coming from your side. So your microphone on the mute. So what I have done is here I have plotted these two expressions for the case when A is equal to 1 and sigma n also is equal to 1. And this likelihood function is in blue, this one is in red. And so this is how it looks like. Now, even before we get into the math, you will see that as we go along this r-axis from some negative values and come towards 0 and then go towards positive values, you will see that in this region, red is bigger than blue. Red is always bigger than blue. At -1, it is also bigger than the corresponding value of blue. So all this time, the likelihood function for x is equal to 0 wins over the likelihood function of x is equal to 1. But as we start approaching r equal to 0, then they both start becoming similar. At r equal to 0, they become equal. And then as r becomes positive, now this likelihood function, the one in the blue, starts becoming bigger than the one in the red. So if I take the vertical values along the y-axis for any value of r which is positive, the red is always going to be smaller than the blue. And so if we are just trying to maximize the likelihood function, which is what the maximum likelihood detector does, it will all obviously say that I will look at the point at which they intersect, they become equal. On the left-hand side of this intersection, the red is bigger than the blue, and so I will say that x is equal to 0 was transmitted. Otherwise, I will say that x is equal to 1 was transmitted. So that is how even visually, pictorially, we can say that r equal to 0 is the decision bound. Now, mathematically, the way to see that is we just take the ratio, the likelihood ratio, and we plug in the two formulas that we have already defined earlier. Now we will see that in this ratio, this part is common, so it obviously cancels out. Also, if I expand the term inside the exponent, a lot of the terms are going to be similar. First, I removed this square root of 2 pi sigma n squared. So I'm left with just the exponents. And if I expand out the exponential bracketed terms, what will happen is r square plus a square, all of them are going to be common between the numerator and the denominator. They will cancel out. The only part which will not be common is negative 2 times RA divided by sigma n squared. Because over here it will be having minus sign, over here it will be having, in the denominator, it will be having plus sign. So I can just simply add them up, and that negative 2RA becomes negative 4RA once I add the contribution coming from the denominator. And so the final answer of the likelihood ratio is just that it is an exponential function of 2 times R times A divided by sigma n squared. So whenever this is greater than 1, I will say that x hat is equal to 1. Otherwise, I will say x hat is equal to 0. So here I have plotted the likelihood ratio. And you will see that the two likelihood ratios both become equal to 1 at r equal to 0. So again, we are leading to the same conclusion. By the way, this also says the belief or the confidence that we have in our decision. If we are very close to r equal to 0, we have pretty much no confidence on what we decide. If we are slightly on this side or slightly on the other side of the decision boundary, the odds or the likelihood ratios are going to be very close to 1. And this we have said earlier also that whenever the likelihood ratios are close to 1, the receiver is most confused. It may make a decision, but that decision is going to be pretty non-confident. But as you move away from the decision boundary, either on the left or the right side, then the likelihood ratios either become very high or become very low, which is a sign that receiver is becoming increasingly more confident, which means that the chances that it will make a demodulation error will also reduce. Okay, so the trick now that we are going to play is that instead of comparing the likelihood ratio to 1, we will do what is known as log likelihood ratio. And it turns out that comparing likelihood ratio to 1 is same as comparing log likelihood ratio to 0. Because if I take log of both the sides of this test, LRT, the likelihood ratio test. So here I took the log of both the sides. The right-hand side becomes 0 because log of 1 is obviously 0. And the reason I'm doing log is because I want to cancel out this exponential function also. So when I do the log of an exponential function, it cancels out. And all I am left with is 2RA divided by sigma n squared. So if I compare that to 0, it is equivalent to comparing R to 0 because A and sigma n squared are given constants. The receiver already knows them. So it can move them on the right hand side, and there they get multiplied by 0, so nothing changes, which means that we are comparing R against 0. So this is the final decision rule that we derived mathematically. We have already seen how this can be visually appreciated. Okay, so in your earlier lab, I don't know, maybe it was lab 2 or lab 3, I had asked you to do all this math yourself. See, this part is pretty simple. It is just the likelihood functions. At that time, we had already said the Gaussian PDF, so this was pretty straightforward. This is just pure math. Any high school student can do this math. So up to this part was pretty straightforward. And if you had stopped here, I would still accept your answer. So that this is good enough. If you say that you derived lambda as exponential function of 2RA divided by sigma n squared, and then you compare it against 1, that is okay. That is good enough. But I also wanted to see if some of you take this next step and further simplify that expression so that you can say that the decision rule is just simply comparing R against 0. And I saw that in your lab reports, many of you did actually take this extra step. Okay, now remember I had asked you that you on your own, even maybe without looking at this at the slides, you may want to repeat the same derivation for on-off keying. I've already given you the answer for the on-off keying, that the decision boundary becomes A divided by 2. It is not 0 anymore. So derive that using the same approach. Okay, so that will give you a confidence on what we are talking about right now. Now, you will notice that there is a great similarity of this likelihood ratio or the log likelihood ratio receiver with a minimum distance receiver. And so what this minimum distance or minimum Euclidean distance receiver does is it calculates the squared Euclidean distance d1 squared and d0 squared. So what are this? These are just the square distances of R with two transmitted symbols, plus A and minus A. And this receiver is a minimum distance receiver. So whenever d1 squared is less than d0 squared, the receiver decides that x hat is equal to 1. Otherwise, it says that x hat is equal to 0. But you will see that d1 square is nothing but r minus a whole squared. R minus a is the distance between r and plus a. And d0 square is nothing but r plus a whole squared. This is the Euclidean distance between r and minus a. Now, you know, this part is, you may be reminded of this part. Does it remind you of something, by the way? This expression of d1 square and d0 square? Something that we just now have looked at?
The exponential part in cost and
Yes, exponential part. P of r by x is equal to.
Correct. I think, I mean, multiple students spoke at the same time, so I didn't get clarity, but I think your answer was that this d1 square and d0 square were the terms sitting inside the conditional likelihood functions, right? So, see this r plus a whole squared is nothing but d0 squared. And this r minus a whole squared is nothing but d1 squared. And so when we did the likelihood ratio or the log likelihood ratio, what turned out is that everything other than d1 squared and d0 squared is common for this likelihood functions. Clearly, this square root of 2 pi sigma n squared inverse is common. This exponential function is also common. So that is why we were able to cancel it out using the log likelihood ratio. The log function canceled the exponential part. We canceled this by simple division. We canceled exponential part by taking log function of the likelihood ratio. This 1/2 also got cancelled. The sigma n in the denominator also got cancelled. So what was unique between x is equal to 0 and x is equal to 1 is just one was d1 squared, the other was d0 squared inside the exponent. The other only difference that is present is that for likelihood ratio or the log likelihood ratio, we were trying to maximize that function. But because of this negative sign inside the exponent, maximization of this likelihood function becomes same as minimization of the distance function. And so this no wonder gives us the same answer that the likelihood ratio gave. If we expand out d1 square minus d0 square, it becomes 4RA. And therefore, finally, our answer becomes the same. R equal to 0 is the decision boundary. So this is what we will, I mean, this is what in the estimation and detection theory, even in machine learning theories, this is what we repeatedly observe.
Sir, I think there should be d0 square minus d1 square.
Sorry, can you repeat again?
Means, sir, in second part after therefore there is if If we have to write a d1 square minus d0 square, then final answer will be minus 4RL.
Answer minus 4
Yeah, sorry. This should be minus 4. And so then when we do d1 square is less than d0 square, this negative term goes away. Thanks for the apt observation. Okay, so what I was trying to say is that from the perspective of estimation theory, a lot of the times the detailed mathematics of the Bayesian detection scheme kind of boils down to doing just the minimum distance detection. And minimum distance rule, we saw here that it is completely, mathematically completely equivalent to the Bayesian rule when the noise is Gaussian. Because it's only when the noise is Gaussian, this d1 square and d0 square are nicely sitting inside the exponential function. If the noise is not Gaussian, if the noise is uniform, for example, uniform distributed, or it is exponentially distributed, or it may have some other probability distribution function. It may be a short noise, it may be an impulse noise. All of those different types of noises are not Gaussian distributed. Then you will not be able to establish its equivalence anymore. And then the optimum Bayesian receiver will actually end up being different from the minimum distance receiver. There is another case where the optimum Bayesian receiver will be different from minimum distance receiver, even if the noise is Gaussian distributed. Who can tell me when that will happen?
So when Q is not equal to 0.5.
What is not equal to 0.5?
Q, the probability of x is equal to 0 or x is equal to 1.
Good. Yes, Taran. When Q, the prior that we have assumed to be equal, when it is not equal, then it can be that minimum distance receiver, which will always say that R is equal to 0 is the decision boundary, is not going to be optimal anymore. In fact, when Q is very different from 0.5, it may happen that suppose Q is very large, maybe Q is 0.9 or even larger, 0.95. It may happen that instead of drawing the decision boundary here at R equal to 0, we may end up drawing it all the way over here, maybe at R equal to negative 2.75. I'm just making up these numbers. But the point I wish to convey is that when Q is really skewed, it is not 0.5 at all, then the decision region for bit 0 might actually include decision region for bit 1 might actually include the voltage that you transmit for bit 0. Right? -1 is the value that we are using for bit 0. Even if you receive -1, you are still going to say that bit 1 was transmitted. Because you are highly prejudiced with the transmission of bit 1.
Sir?
You know ahead of time that it is bit 1 which is most of the time getting transmitted. And so even if you receive some highly negative values, you will still not change your mind that bit 0 was transmitted. Only after you start getting values which are very large negative numbers, maybe -3, -4, that is when you will change the mind and you will say that bit 0 was transmitted. So this type of strange situations can also happen, that the decision region for bit 1 might actually include the constellation point for bit 0. But and so this is obviously not the minimum distance decoder anymore. But apart from such strange cases, which by the way, they arise in the real world, okay? I mean, that is what we repeatedly have said in the context of that C disease problem, right? In the C disease problem, the prior on x equal to 1 was pretty small. I don't remember, maybe the value we had taken was only 1% or something. By the way, in the month of April, that prior was not 10%, okay, or 1%. It was pretty much everybody was getting that C disease. And so prior was pretty high, actually. I mean, in my case, it was exactly the opposite. Even before I went to do my coronavirus test, I knew that I had coronavirus. So even if the test had come out negative, I would have said that the C or X is equal to 1. So I was prejudiced exactly in the opposite way, which is not where you want to be. To be happy, you really want X equal to 1 to be having very small probability, at least for this C disease problem. But okay, that is a little bit on a lighter vein. Coming back to the theory and taking this more seriously. See, although this is the case, that the minimum distance decoder and the Bayesian decoder, they become identical only for the Gaussian noise channel and only when the priors are equal. Even then, this minimum distance decoding finds a lot of application in the machine learning community, in the communication theory, in the estimation and detection theory, in the learning algorithms, etc. And actually, we have already seen one such technique earlier. Who can tell me that? Where we were actually applying the same idea of minimizing the distance.
Hamming minimum
Yes.
decoder.
Correct. Exactly. So if we generalize and say that, okay, we in general are kind of talking about distance. It may not be Euclidean distance, but in that case, it was the Hamming distance. Then minimization of the Hamming distance was the rule that we had used for defining those Hamming spheres and for defining the detector of the Hamming code. And even when we looked at in the last lecture only, when we proved why the information transfer that IXY gives the lower limit on, the upper limit on the channel coding rate. That time we had looked at the typical set formulations. And again, that time we had said that the receiver would be doing the minimum distance decoding. So that is how the minimization of the distance is a very common technique. It is getting used in multiple different domains. And it is not that why are we minimizing the distance becomes the question. Okay, typically minimization of the distance is considered a good thing to do. The trick is in defining the distance. For modulation topic, the distance is very easily defined as Euclidean distance because we are dealing with the numbers on the real line, the real number line. For the channel coding, we were not dealing with the actual real valued numbers. And so we had to define the distance, the concept of distance more carefully. And that is where we came up with this Hamming distance concept. But in many other contexts, for example, in machine learning, you are trying to compare two images, right? Today in Google, you can actually input an image as your search query and it will fetch all the other images that are similar to it. Essentially, it is doing minimization of distance. But now that distance minimization is what type of distance minimization? Do you do Hamming distance minimization? Where you take each pixel of an image as forming zeros or ones, and then you do just basically Hamming distance minimization. Do you do that? Or you define distance function in a more elaborate manner? That is what the challenge is. See, artificial intelligence is, in a way, it is artificial because our own intelligence, the human intelligence, calculates effectively the same distances. But the way it does that is a mystery. Nobody knows how our brains calculate the distances. If somebody got an answer to that, then that person can launch a company which will be even bigger than Google or Apple or Microsoft. So that mystery is what is about the definition of distance. But minimization of the distance is something that we all are, again, intimately familiar with. So that reminds me, okay, we still have about half an hour. So I'll kind of, again, do a little bit of non-technical sidetrack, and I'll give you a story that will hopefully show to you this distance minimization that happens in our brains. So, when I was growing up, I had a lot of neighbors, a lot of friends. So there was one family, family of 4, parents and the son and the daughter, that we used to know quite well. And not only I would know children of my age, but even my parents were friends with their parents. And so, as it happens in after the dinner at the night time, 2 families would get together. And so one time we were sitting together in our house, in our living room. And then, a lot of conversational topics were going on. Then suddenly the dad of my friend said that, today actually, or a few days back, a funny thing happened. We all went out to see a movie. That is what my neighbor's dad was saying. They went out to see a movie, and in those days, obviously, there were no Netflix or YouTube, so everybody has to go to a theater. And then he said that once the movie was over and we walked out of the theater, we were walking back to our home, and we all suddenly said the same thing, that the heroine, the actress, the main character of the movie, reminded them of somebody. Okay, so it was not that just the dad thought that, the heroine looks like someone, but even the mom thought that way. In the son and the daughter, they all thought that the heroine looked like somebody. But then when the question came who she looked like, nobody knew the answer to that. So they were scratching their heads. And so they returned back home and they were at the dinner table. And that was kind of the question that was running at the back of their mind. They probably spent a few minutes trying to actively think of who she was getting reminded of. They didn't know the answer. And then after the dinner, they wrapped up the day, they went to sleep. And in those days, a lot of the times, especially in the summer days, you all get together in one big room, put your mattresses and sleep. All 4 of them were sleeping in the same room, turned off the light. And then a few hours passed, it was midnight. And at the midnight, the stroke of the hour, the girl, the daughter, she was sleeping. she suddenly stood up. She came to a sitting position and she screamed, "Heroine, oh, you know that heroine looked a lot like the cousin of the nephew of the dad." Okay, somebody, some distant relative. And so the other three family members, they were all asleep. They kind of woke up, and probably they had mixed feelings. In one way, they were happy that yes, they finally got the answer to the puzzle, and they all agreed yes, the girl's answer was correct. But maybe they were a little bit angry at the girl also, that why did she have to disturb their sleep? Maybe she could have said the same thing next day morning. Anyways, the point is that what was going on in the brain of that girl, even when she was falling asleep, was minimization of distance. And that distance minimization was a difficult task for all four of them. But the daughter's brain solved it just as when she was about to fall asleep. And she said that the distance gets minimized when I consider the cousin of the nephew of my dad. Okay, so that is kind of showing a real world example of type of distance minimization that happens in our brains all the time. And that is what I was trying to say, that, you know, the algorithm that ran inside that girl's brain and the algorithm that runs inside all of our brains for all different contexts, all different or many different such situations arise, that nobody knows. And the part about that algorithm, how to minimize the distance is not a big deal, but how to define the distance is this part where the answer is not available. Fortunately for the modulation topic, the distance is very easily and nicely defined, simply as the Euclidean distances. Okay. So now let us move forward. Let us also complete this discussion by deriving the probability of bit error. And there the main concept is that once we have defined the decision boundary, the bit errors happen whenever this received voltage R falls on the wrong side of the decision boundary. And so all we have to do is to integrate the conditional PDF of R given a particular transmitted symbol for half of the real valued line. And so that math is what I am writing here. But whenever we do the math, we have to be more complete, right? Although we may know the idea, the concept, we have to go through proper derivational step. And so what we are trying to do is determine that error is equal to 1. And the way we will do that is we will apply this marginalization of the joint PDF. And so we'll consider the joint PDF of X and E. And then we will marginalize it over X equal to 1 and X equal to 0 by keeping E to be constant 1. Now this joint PDF can obviously be written as the product of the prior and the conditional PDF. Conditional of E equal to 1 given X equal to 1 and E equal to 1 given X equal to 0. So this is just the alternate way of writing this joint PDF. But prior we have already said we are assuming it to be 50%. So this P of X equal to 1 and P of X equal to 0 comes out, and then inside the bracket remains only the conditional PDFs. Now, we know that the receiver makes an error, E becomes equal to 1, when X is equal to 1 is transmitted when R is on the wrong side of the decision boundary, meaning R is negative. And similarly, when X is equal to 0 is transmitted R falls on the wrong side of the decision boundary when it is positive. So this is what we had said on the previous slide, that we have to simply integrate the conditional PDF for half of the real valued line. And so this probability evaluation is what I have done here. This is the conditional PDF of R when minus A is transmitted. And then I'm integrating over the positive real valued line from 0 to infinity. Now it turns out that this complicated looking integral has a kind of simple answer, which is known as Q function. Now, Q is not a typical type of function, it's not like a square or square root or logarithm or exponent. In fact, Q is this whole thing. So, so you can't actually write some simple formula for Q. You have to actually numerically solve this whole integral. But still, it is this Q function is used everywhere because people have come up with the tables, right? A function is actually ultimately a table. If you apply some x, what is the corresponding of the function output y? So you put it in a different column. X is in one column, y is in another column. All the possible values of x are in the first column, corresponding values of y are in the second column. And then you just do a table lookup. Whenever you get a particular value of x, you go to that row of the spreadsheet and you figure out what y is. So that will avoid all this complicated numerical integration. That is what Q function does. In MATLAB or in Python, when you call Q function, it actually does this type of previously computed answer, and it gives you the final answer. So all of that detail has been already done for us, and therefore we can simply make it like a well-known function. Now it turns out that so we currently evaluated this part here. You can do the math yourself and you will see that the second conditional PDF also is same, Q of A divided by sigma n. And so when you add both of them together, you get 2 times Q divided by sigma n, Q of A divided by sigma n. And then after you multiply by half, the final answer becomes just Q of A divided by sigma n. So this is the probability of demodulated error. Okay, so we still have about 20 minutes. Let me take just a few 1 minute or 2 minute break. I'll be back and then we'll do a few more slides. Okay, so so this is going to be a little unique way of studying the topic of modulation. If you study a textbook or maybe any other reference, maybe a YouTube video or anything like that, maybe you will not see this approach. But there is certain benefit of doing this way. The reason we are calling it to be a simplified model is because the modulation is intimately connected to electromagnetic waves. That is what we have said earlier. And so typically, you first learn about how the electromagnetic waves are getting modulated. And then you come to the Bayesian framework. Instead of that, we are starting with the Bayesian framework and just ignoring the electromagnetic wave part of it. And that is why we are calling it the simplified model. And there are certain benefits of learning the topic of modulation in this manner. And so let us see what this simplified model gives us. Actually, we are going to be able to cover a lot of conceptual ground using this simplified model. So one benefit is that for the BPSK, we have seen how the bits are getting mapped to the voltages. And specifically in the modulation theory, there is some conceptual visualization which is known as constellation diagram. And this simplified model allows us to picture that, allows us to draw those concept diagrams. And so the constellation diagram is what I have drawn here. See, in this example, bit 0 got transmitted using 1 volt. A is equal to 1. And therefore, bit 1 got transmitted using plus A, meaning 1 volt. Bit 0 got transmitted using minus 1 volt. And so all that this constellation diagram does is it puts 2 dots at plus 1 and minus 1 volt. The good thing about this constellation diagram is that it summarizes what the modulator is doing. And also, there is a very important parameter called it transmit symbol energy, E of S. E of S is nothing but essentially it is the square of the voltage. Actually, it is a little more complicated than that, but for the time being, we are going to take it as square of the voltage corresponding to that symbol. And so in this case, it is just the square of the Euclidean distance of the constellation point from the origin. So again, this Euclidean distance way of defining this symbol energy, E of S, is something that we can right away see from this constellation diagram. And again, I want to emphasize the Euclidean distance aspect of E of S, because it again will help us to define the detectors of more complicated modulation schemes. So this is the constellation diagram of BPSK. Now, why is it called constellation diagram? Any guess? This is not a technical question. Those of you who are good in English may know the word constellation. In what context does it get used?
Different voltages we obtain, so
No.
Looks like a star in the sky,
Sorry?
similar to the. Just sir,
Feel like
we
pattern of stars.
Exactly. Very good. Right. So when you look at the night sky, the pattern of the stars that you see in the sky is called constellation of the stars. And so in some rough analogy is that these 2 points are like 2 stars in the sky. So that's how people came up with this name, constellation diagram, and that name is stuck. It is very well-known terminology in the communication theory. Now, the other thing is that using this simplified model, we were actually able to model what the real world noise channel does. A lot of the time, the real world noise channel is indeed Gaussian. So we were able to realistically model what is going on with the channel itself. And then finally, we can also visualize what happens at the receiver. So when, suppose bit 1 got transmitted, so the transmitter sent this blue point, and then the receiver added some negative, the channel added some negative noise. And so you might end up getting a voltage which is somewhere over here. Let's say. Then after some time, the transmitter sends another symbol, and the receiver ends up observing a voltage value somewhere over here, maybe, because the channel introduced slightly positive noise. And if you keep on looking at what the receiver observes when the transmitter sends one, maybe 100 times or 200 times, then you might see that you get a lot of such red points everywhere, scattered around the blue point. Hopefully these red points don't go very close to zero, but who knows, if the noise is large, when you transmit this blue point, the noise is very large negative value, maybe negative 0.7, and you might end up getting a point over here. But fortunately, it is still on the correct side of decision boundary. And so you will still decode this receipt voltage as x equal to 1. Similarly, when bit 0 is transmitted, most of the time, hopefully, you will end up getting some points which are like over here. And a few times you might get some voltages which are here. So if you do this type of measurement over a lot of symbols, then maybe your diagram might end up looking like this. So this is also a very common diagram that the engineer of a communication system has to deal with. At the transmitter, it is just the constellation diagram. At the receiver, what you end up seeing is some fuzziness around the transmitted constellation. And that fuzziness, some blurring, is coming because of the noise. And the engineers can actually determine the power of the noise or the variance of the noise, which are one and the same thing, by looking at the spread. If the spread is very small, then we know that sigma n squared is likely to be very small. If spread is very high, then sigma n squared would be higher. And again, there is a terminology called EVM, or error vector magnitude. So all that it does is it takes the difference between blue point and each of the red points. That is called the error vector. Then it takes the magnitude of that vector, and then it averages it out over all of the red points. And that somehow becomes an estimate of sigma n, the standard deviation. Anyways, so this is something that is very commonly used tools and techniques of the trade. And we can appreciate all this concept, the constellation diagram and the error vector magnitude and all that, without having to worry about any complex aspect of the modulation theory. By just considering this simplified model, we are able to understand this. The other benefit, obviously, is that all that we have done, the decision region formulation, the form of the optimal receiver, and even the an understanding that the optimal receiver minimizes the distance, is all possible using the model that we have studied. And in the case of the diagram that we had looked at earlier, by the way, here I unwittingly changed the colors. The blue of the previous slide has become red and the red has become blue. So please bear with that. So what we are saying is that the minimum distance receiver, when it gets a particular value of the received voltage R, let's say this particular voltage, then it calculates the vector from each of the two possible transmitted constellation points. So this becomes E1 and E2. And it will select that constellation point for which the magnitude of this error vector is the smallest. And so it will say that when you get a particular point such as this, you're going to say that bit 1 was transmitted. Okay, so this is a way to visualize the minimum distance receiver. And using this, again, we can say that if anytime the blue point is on the right-hand side of the green line, the decision boundary, which is r equals 0, that blue point is obviously going to be closer to this red point compared to that red. The other thing that this simplified model has allowed us to do is we were able to do the theoretical evaluation of the performance in the Gaussian noise channel. We just now did that. The answer comes out to be Q function of A divided by sigma n. The good thing is that once we have the theoretical formulation, we can compare our actual receiver, how it works. Maybe there is some problem in the receiver. Then if we can do the experiment on the receiver, maybe you take your Wi-Fi modem, unplug it and put it in the lab and calculate the bit errors produced by this Wi-Fi modem. You compare it against this theoretical curve. And if they are close or on top of each other, then you know that your modem is working fine. Alternatively, in the absence of having such a laboratory framework, you can do a computer experiment, which you have already done in one of the labs. You run Monte Carlo simulation of a BPSK receiver that you would have implemented in MATLAB, and then compare the bit error rate of that simulation with this theory. And this is going to give us an idea of how that simulator is. Again, remember the theory is integrating the conditional PDF on half of the number line. So you do integration over either the green part, which is shown here, or the blue part, which is shown here. And either of those two will give you the same answer, which is Q function. And if everything is working fine, you will see that the theoretical expression, which is the the red curve, and the simulation, which is the blue points, they will match very well. And so this kind of gives you a satisfaction that what you have done is correct. The answer that you get through your simulator matches the answer that you derived using a completely different method. Okay, I think this is where we are going to stop for today. And we will continue on this modulation topic